jolly good. All right, the talk today is actually about some of the work that, where's the,
all the way to the top, the small one.
the tiny one. Oh, there we go. All right, so the talk that I'm giving today is actually a collaboration between Ahmed Naguib at Michigan State University and I'm killing the pointer. There we go. I got it. There's actually a switch here. Anyways, doesn't really matter. And Jonathan Morrison at Imperial College. And in fact, all the experimental results I'll be showing were taken at Imperial College. The main reason why we got interested in this particular problem is what we ultimately want to try to do is develop controller systems for controlling turbulent boundary layers. And the key word here is that we want to do that in the laboratory. As most of you can probably appreciate, that's actually quite difficult to do, and we're a long way from being able to do that. So we thought we'd try to start with a simple linear model, which might be representative of turbulent boundary layers, and try to see if we can actually implement that and learn something from that simple model. And then, so we had to look at this transient growth problem that we've heard about quite a bit this week. And it turns out that it's basically a physical model of exactly what we're trying to do. So the optimal perturbations for this transient growth takes the form of these span-wise periodic streamwise vortices, which lead to these high and low speed streaks. So this is kind of a flow visualization from Matsuberra and Alfredson, and you can kind of see the resemblance to what one finds close to the boundary in a turbulent boundary layer. Now the actual connection maybe can be made more formal between these two particular problems if we look at it from a controls perspective. So if we take the Navier-Stokes equation and linearize them in such a way that we end up with the Orr-Sommerfeld-Squire equation, and this is just written in sort of state space form. This is fairly standard. And then we have this nonlinear term which is added to that. So this is a form of the equation that resembles what John Kim was presenting yesterday. And basically what we find is that the nonlinear term are actually conservative with respect to disturbance energy. Basically all it does is it redistributes whatever perturbation or disturbance is present in the flow. So if we use the passivity principle, then we can sort of write the linear part of the equation as our plant G, and then the nonlinear part is just essentially like a noise disturbance to our system. So we can actually, in theory, apply a controller K, which would then make this linear part of the loop, and K, the key point is K is actually a linear controller. So we can make that part of the controller actually passive. So essentially what that ends up doing is we stabilize the whole system about a stable state, and that can be done fairly easily in a closed or periodic domain. Of course, there's some complication if we want to do that in a spatially growing turbulent boundary layer. But in the case of transient growth, we can do some fairly big simplification where that nonlinear bit just gets thrown out of the problem. So we can design a controller which hopefully will have some sort of relevance to a turbulent boundary layer. So if we go a little bit further in terms of describing the controller system that one might obtain, so this kind of a cartoon-like depiction of what we have. So you've got some sort of disturbance coming in here in the boundary layer, and that's being sensed by some form of sensor array. It doesn't really matter what that is at the moment. And then hopefully you get some estimate of what the state is above the wall, and then you use some sort of model to sort of describe how that disturbance will evolve over a particular domain or subdomain of your plate. And then the controller makes some sort of decision about what signal to send to the actuator. Again, the actuator doesn't matter what it is at the moment. In theory, we can change that, and then all we do is change the boxes here. And then that does something to the flow, the Navier-Stokes being the real flow. And then you end up with some sort of disturbance that's left over at the end. Hopefully your controller is driving that to zero. But in reality, there's all kinds of uncertainties and errors that might be associated with, say, the model reduction, for example, or noise in your sensor. So actually what we end up doing is we add to the feed-forward controller a feedback controller, which basically does the same but backwards. And that really increases the robustness of the whole control system. So that's kind of the approach that we want to take as far as the control of this boundary layer is concerned. So, but the talk here today is actually going to focus on establishing this sort of experiment where we're actually producing transient growth in somewhat of a controlled manner. By controlled manner, I mean that we are actually want to perturb the flow in such a way that we have, we know the disturbance that we put in, and we know how that evolves. And you know, being a researcher, while I'm at it, I might as well learn something about the physics and hopefully develop a better model to put into that earlier box. That model box is kind of what we'll be talking about today. There's a number of a few ways that one can actually do these types of experiments, but one of the standard ways to put these little roughness elements in a sort of span-wise periodic fashion. And the sort of important parameters here are the roughness height k, the diameter d, and the spacing delta z. And essentially, the roughness elements end up creating these standing streamwise vortices here, which approximate the optimal growth perturbation. And then that generates this liftoff process where low momentum fluid gets lifted off away from the wall and high momentum fluid moves towards the wall, so you get these high and low speed streaks. And there's two particular studies that are particularly relevant to this talk, really, is the work of White and his co-workers, and he's got a few papers on the topic, but also Frentzen and et al. And basically the main difference between these two studies is that in the case of White, the initial perturbation is actually quite weak. As a result, he ends up with low speed streak, and that really low speed streaks downstream of the roughness element. And that contrasts quite dramatically from the work of Frentzen, where the perturbation is much stronger. In this case, he gets the high-speed streak, as illustrated here, downstream of the roughness element. Essentially, what's going on is you get a wake mode, or you get a velocity deficit due to the wake behind the roughness elements. And if that wake mode is relatively weak compared to the roller mode, those streamwise vortices, then you end up with the velocity deficit remaining behind the roughness element. And I'll show some example of what I mean by that. But basically, we've designed our experiment such that we've extended quite dramatically the parameter space span by these types of experiment. And we've also taken particular care to make sure that we actually straddle the two experiments. So we see where that transition between a wake-dominated perturbation or a roller mode dominated experiment comes in. So the experiment looks a bit like this. These pictures are a little bit dark maybe, but basically this is a cast aluminum plate that's been polished, so it's extremely flat. It's been mounted vertically in the 3x3 tunnel at Imperial College, and the reason why we use the 3x3 is the turbulence intensity is extremely small, about 0.05%, which is very important for these types of studies, which are extremely sensitive to outside perturbations. We've put a little a roughness plug about 200 millimeters downstream of the sharp leading edge for a plate. And the key features of that plug, which you sort of see in a diagram here, is that we can actually adjust the roughness height anywhere between 0 and 2 millimeters. So that's allowed us to change the strength of the perturbation quite easily. But also we can change the spacing between the roughness elements and set it to anything between, set it to either 10, 20, or 30 millimeters. And so we've used that to carry on a fairly extensive parametric study, which includes 8 cases, and that's shown here. And then we've got a few other miscellaneous cases. But the measurements were taken using a normal hot wire to take the streamwise velocity. But we've also used a combination of the normal and a slanted wire to try to get measurements of the span-wise velocity. So if you get a plane measurement of the U and W, you can actually infer the wall normal velocity through continuity, and that's never been done before. So the idea is to try to get some feeling about what those perturbation that we introduce actually look like. Anyway, so the parametric study itself is we've focused on looking at the effect of the roughness height, the Reynolds number based on delta, the beta parameter, which is basically the wavelength at which you introduce the perturbation in the first place, but also we've looked at changes in the diameter of the roughness elements. So in the first instance, we need to make sure that the perturbation that we do introduce is small enough such that the assumption of linearity can still be still holds. So one way of doing this here, I'm basically showing the velocity profile. So the U here is actually the velocity profile at various span-wise locations that I've averaged, and basically they're indistinguishable from the Blasius profile. So I didn't even bother with the legend here, and that's sort of confirmed by the if we look at the H factor at various X location. There's some deviation here from Blasius, but that's kind of expected since very close to the roughness element, there'll be some sort of nonlinearity, but that decays fairly quickly. So over the range of streamwise positions that we're interested, linearity actually holds. So here I'm looking at the disturbance velocity normalized with the free stream velocity, and so these are isocontours of that as a function of the span-wise direction through the boundary layer thickness. And this little black box here represents where the roughness element actually is. So in this case, we do find a high-speed streak downstream of that roughness element, and it's straddled by two low-speed streaks on either side. And for this particular case, actually, the disturbance energy is always decaying as we move downstream. But you can see that it's clearly a fairly single modal type disturbance that we've introduced. And if we can compare that to case 9, which is actually a much weaker this perturbation that we introduce in, you can see at 300 millimeters downstream, there's still evidence of that wake mode. So there's that low-speed streak downstream of the roughness element, which is straddled by the two high-speed streak generated by those counter-rotating vortices. And as you move downstream, the roller mode takes over the wake mode, so those two streaks merge together, eventually create only one high-speed streak. So if we now look at the profile of the RMS of that perturbation in a span-wise sense as a function of the wall normal direction, in this particular case, at 250 millimeters, the energy is that curve here. And as you move downstream, the total energy grows before it starts to decay. So that's that transient growth before viscosity takes over again, and you get that viscous decay. But maybe the thing to note here is that optimal growth theory predicts that the optimal disturbance should be at 2.1 here. And so we actually introduced the perturbation a little bit closer to the wall than what we'd like to do. But as you move downstream, it tends towards that optimal value. Now, if I look at the distribution of the energy as a function of the modes, if you will, the span-wise wave number, which is that kz, in this particular case, all the energy is basically at that single mode. There's a little bit of energy at the higher harmonics, but that decays quite quickly. And this wave number is actually associated with the spacing of the roughness element. So this is actually saying that the disturbance energy is at the wave number at which we introduced the perturbation in the first place. So what we'll be interested in is actually looking at the evolution of that energy as we move downstream and see if we can actually do some sort of predictions about that. So I'm going to define this energy at the wave number delta z, or wavelength delta z, which is basically just going to be that power spectral density for that wave number. So if I plot that for all the various cases that I have, well, I end up with a little bit of a mess. But here it's plotted as a function of beta square. And for those who wonder why we do beta square, it's actually the x location normalized with the disturbance energy itself. And here I've normalized it with the Reynolds number based on k squared, and REK is defined here. So it's based on the roughness height and the velocity at the top of the roughness, so at y equals k. and it's sort of a reasonable collapse, but really there's a lot of noise. But further downstream, where it's all decaying, there's no collapse whatsoever, which isn't really surprising, because you sort of expect that the terms that dominate in the boundary layer equations are different when your energy is growing, because in this case it's a inviscid perturbation, so the viscosity should be thrown out. But later on, you don't have that V disturbance, so you only end up with viscosity. So if you look through the equation, it seems to make sense that the scaling for the growth and decay region should be different. But in fact, if you do that, or when I did that, turns out that the energy growth should actually scale with REK infinity. So now we're looking at a velocity scale, which is U infinity as opposed to UK. And the difference between that graph and the other graph is the dependence on k to the fourth or k to the power squared. So it's fairly strong difference in terms of how sensitive it is to the roughness height. And one may argue that I get slightly better collapse, but it's, obviously there's something we're missing here, and I'm still scratching my head about that. And I was kind of hoping to get a nice, straight line across, but I'm not giving up hope quite yet. So anyways, in conclusion, we've established this experiment to look at transient growth and the control of transient growth. And in the process, we've performed an extensive parametric study of it to look at the effect of the roughness geometry. So the present study extended the parameter range of previous studies, so we've shown that transition between the two main perturbation modes. And really, the wake mode is only relevant close to roughness element. And in fact, you sort of expect that the roller mode is the one that's associated with what we understand to be transient growth. So really, as far as the controller is concerned, that's what we want to control, is the roller mode. The wake mode seems to be this nonlinear effect that comes in. And then, while the physical model has proved to be elusive to find, but I'm getting there, so I'm not giving up. Anyways, thank you very much.
Question?
Yeah, I'm not sure if I understood you correctly, but you didn't get this R squared scaling, I guess. This is what one of your last slides. And you were wondering why. I guess it's because possibly the disturbances are not optimal, and then you would expect the optimal scaling, maybe. Is that a simple answer, or is it something else?
I'm hoping it's that it's a different scaling, that we'll find that scaling. But it's probably just slightly more complicated. But you're right, the perturbation that we put in is suboptimal. So that, even if we do find the right scaling, I do expect a significant amount of scatter.
You could try to characterize your disturbance and then see in the linearized equations what your disturbance would give, what scaling that would give, and then maybe you would get. Because if you have something different than the optimal, you wouldn't really expect the optimal scaling, I guess.
Yeah, it's a good idea.
Any other comment, question? Okay, thank you again.